Programmers are weird. Okay, let's say 13. So sometimes you run into packed data structures. And what I mean by that is it's not like those extents we saw earlier, where each part of the extent was like on an even byte boundary, right? We had 4-byte fields and 2-byte fields. What I'm talking about is where like a single byte, for example, might represent multiple values. So we talked, for example, about Linux and Unix permissions, right? And I said that there were 3 groups of 3 bits for owner, group owner, and others, right? Turns out there's a 4th set of 3 bits, which is where you put things like set UID, set GID, and sticky. So actually, the Unix permissions field is 4 3-bit values, so 12 bits. Those 12 bits are actually packed into a 2-byte field with an additional 4-bit field to get you to 16 bits. That is the file type, right? And so like if you actually unpack it, you see the 4-bit field, which is the file type, followed by the 4 3-bit fields, which represent the various permission bits. Okay. And so you have to unpack that to understand what the actual settings are. This comes from a time when memory and disk space were much more costly and in short supply than they were today. So, the first server I worked on had 2, for the time, very big hard drives, each of which stored 327 megabytes of data. I mean, we were styling, right? So we had, over 600 megabytes of storage online. Each one of those drives weighed 80 pounds and was the size of a large hard-shelled suitcase. Yeah, I was just browsing around on social media while you all were working on the exercise. SanDisk has released a 1.5 terabyte micro SD card, right? So in something the size of my pinky fingernail, you can store 1.5 terabytes now. So things have changed since 1985. Yeah. So let me give you an example of this. syslog on Unix. Okay, so messages in the Unix logging system are identified with what we call a facility and a priority value. And those facility and priority values are packed into a single byte, which is transmitted over the wire with the syslog message. Okay, so the upper 5 bits are the facility number, right? And in this case, that 5-bit value is 10, right? 8 plus 2. Right? And facility number 10 happens to be what the Linux people know as the auth probe facility, which is where all the security related messages go, like people logging in with SSH or on the console of the machine, sudo messages and all that stuff. That's all goes to auth probe. So this is actually a fairly common facility number in Linux. The lower 3 bits of the byte are the priority values. So there are 8 possible priority values, ranging from debug, which is 0, all the way up to emergency, which is 7. Okay. This is priority 5, which is notice priority. Okay. So if somebody logs in via SSH, for example, a record of that login is written to syslog at the authpriv facility at notice priority. Okay. So this is an example of a packed byte. You've got multiple fields jammed into that 8-bit value. Now that's convenient for transmission, right? We only need to send 1 byte with the 2 fields in it. But when I want to use those fields, I need to unpack the byte somehow, okay? So in order to do that, like if I want to use the facility value or I want to use the priority value, we've got to somehow extract that field and get it into a byte by itself. And this uses concepts like masking and shifting, which you might have heard of. And I'm going to explain what they are. But basically, we're going to be doing some binary arithmetic. And most of you are like noping out at this point. It's like, nope, nope, Don't want to hear it. Don't want to hear it. It's not as bad as it sounds. Really. I could show you how to do this. It's not terrifying. You can do this. Okay. Okay. Here we go. Let's talk about masking first. Okay. So there's an operation called a bitwise AND, right? You take 2 bytes basically, and you sort of line them up next to each other, and then you just AND the bits together bit by bit. That's why it's called a bitwise AND. You're not ANDing the entire 8-bit value together. You're ANDing the individual bits together one at a time. Okay. Now, bitwise AND is really just multiplication. Okay. But it's bit multiplication. So it's a really simple multiplication table. There's 0 and 1. Well, anything times 0 is 0, right? So 0 times 0, that'd be a 0. Right? 0 times 1, well, that's also a 0. 1 times 0, that's a 0. The only one in the whole chart is 1 times 1, right? So only if both bits are a 1 do you get a 1 back. Think of it like multiplication. Anything times 0 is 0. 1 times itself is 1. Okay, cool. Unless both bits are 1, the result is going to be 0. And so if you use a mask, what you're doing is you're taking a value that's either going to keep or suppress whatever part of the byte you don't want. And we use masks all the time, right? You might have heard of a network mask, right? There'll be some exercises about that coming up, actually. A network mask allows you to pull out just the bits of the IP address that are the network address and not the individual node or host address. So if you want to keep the bits, you use a mask of 1s. If you want to suppress the bits, if you want to make them go away, then just use a 0 mask, because anything multiplied by your zeros is just going to drop out. Let me show you an example so you can understand better what I mean. Okay, so we're starting with our packed byte, right? We got auth priv notice. Now, what I want to do is I want to be able to see clearly what the lower bit, the priority is. So it's the lower 3 bits. Okay. So I want to keep the lower 3 bits and get rid of the upper 5 bits. That means that my mask is going to look like this. I want to get rid of the upper 5 bits, so I use all zeros in the upper 5 bits of my mask. And then I use all 1s in the lower 3 bits, because that's the part I want to keep. So you do a bitwise AND, right? So 0 ANDed with 0, or 0 multiplied with 0, it's going to be a 0, right? 1 multiplied by 0, also 0, right? So this bit's going to go away. That's the power of the 0 mask. Similarly, this bit's going to be suppressed, right? Because even though it's a 1 up here, you're multiplying it by a 0 down here, it's going to go away. Okay, and then we get to the all 1s portion of the mask. Okay, 1 times 1 is 1, so that one bits we're going to keep. There's a 0 up here. I'm multiplying it by 1, but the result is still going to be a 0, so it's going to be just like the original digit up here. And then again, we have a 1, which ended with a 1, gets you a 1, and boom, there you go. By using that mask, we've successfully suppressed the facility number at the top of the byte, and we've ended up with a byte that just has the priority value in it. Now, obviously, you wouldn't write this in code this way, right? The way you see it in code is something more like this. We have the original byte, and if you translate this byte into hex, right, it's 0, 1, 0, 0 is the upper nibble, right? So that's 4 plus 1 is 5. And then we have another 5 down here. So this packed byte in hex is 55 hex. Then we're going to do a bitwise AND operation, which we usually represent with a single ampersand, with our mask. Now our mask is in hex a 0, and then 0, 1, 1, 1, 1, that's 7. So our mask is 7 in hex. And the result is, well, the priority value, which is 5. So this is, I mean, this is the way, you know, a programmer would write it. It's the original byte bitwise ANDed with our mask of 7, and you know, the result is whatever it is. Okay, so that's a very simple example of a mask. Right? You use ones for the part that you want to keep, and you use zeros for the rest that you don't want. Okay. Now let's do the other one. I want to now get at the facility value in the upper 5 bits. So that means I need to somehow take these 5 bits and create a byte with those 5 bits basically shifted down to the right here, right? Overwriting these lower 3 bits. Okay. So we need to move the 5 bits at the top of the byte 3 places to the right. Call that a right shift. And this is actually an operation that's so common, shifting left, shifting right, moving things back and forth. And it's easy for computers actually to do this operation. So there's an operator, shift left, shift right, which allow you to specify the number of bits you want to move your bits. So if we shift right 3 places, what happens? These bits move down to the right 3 places, and the space that they used to occupy before the shift just becomes zeros, which is exactly what we want, right? The operator knows what you're trying to do. So yeah, there's a shift right operator that just says, okay, I want to shift this right, you know, 3 bits, and you end up with the byte you want, a byte that just has the facility value in it so that you can then manipulate that. Programming language, the shift operator is to the right, double greater than signs. Shift left is 2 less than signs. And then you specify the number of digits the number of places you want to shift. Okay. So in our example, we start with that 55 byte, which is the packed structure with the facility and the priority. We shift right 3, right? So the arrows are pointing to the right, and we're going to go 3 places. And the result is this byte here with just the facility value, which is hex 10. A, right? Okay. So again, that's how you'd see it in a programming language. Original byte, shift right 3. The result is whatever it is. So masking, if the bits are in the right position, just mask them and get what you want. If you need to move things around, you can shift them left, you can shift them right. So, for example, I want to go back the other way. I am creating a syslog message, which is going to be sent to auth facility at priority value notice. So I need to create that packed byte with those 2 values in it. How do we do that, right? Again, it is shifting and a little arithmetic. So we're going to start with the facility value that's going to be ultimately in the upper 5 bits. Okay, so we plunk in hex 0A, which is facility 10. Now we need to, in this case, move those bits to the left 3 places. That's a shift left. So shift left 3 gets you this byte, right? So those 5 bits have moved up, leaving behind a bunch of zeros where they used to be. Okay, shift left 3. Now we need to put in priority 5 in the lower 3 bits. Don't overthink this. We just add 5 to the byte, right? And that gets you the final packed byte. So the way you do this is you take the facility value, you shift it left 3, and then you just add the priority value, and you're done. Okay, so let's talk about the first question. So this question deals with CIDR notation. CIDR stands for Classless Internet Domain Routing. So basically, these are the net masks, the new net mask syntax that new. I mean, geez, how long has CIDR been around? Early 90s. Anyway, this is the way we express net mass in the modern era. And it's basically a bit mask. Okay, so if I say /24, that means a 24-bit mask. So IPv4 addresses are 32-bit addresses. Okay. So if it's a /24, the net mask is the upper 24 bits all ones, right? Which, in hex would look like what you see, 0x, FF, FF, FFF. That's 24 bits. And then the lower 8 bits are zeros, okay? So that's a /24. So the question is, given these different CIDR prefixes or suffixes, what are the network masks? Okay, so /16 means the upper 16 bits of the 4-bit byte value are ones. So FF, FF, right? That's 16 bits, right? Remember, each hex digit is 4 bits. Right? So 4 Fs and then zeros in the lower portion of the mask. Okay? /16. /20, okay? 20 bits of ones at the top of the byte. So remember, each nibble is 4 bits. Sorry, each hex digit is 4 bits, right? So 20 bits, ones, 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 ones. Okay, so that's 20 bits of 32, and then 12 bits of 0. Okay? So converting these to hex, we have FF, FF, FF. That's 16 bits, and then another F gets you to 20 bits, and then the rest is zeros. /27. This one is often what your ISP will give you if they give you a static range of IP addresses, right? So 27, okay, so we need 27 bits, 4, 8, 12, 16, 20, 24, and then 3 more bits gets you to 27. Okay, a bunch of Fs, okay? And then in the lower bytes, okay, 1, 1, 1, 0. 8, 4, 2, 14. Okay. And 14 is E. So this nibble is an E, and then the lowest nibble is a 0. So yeah, that's how you do the CIDR stuff. After a while, you just figure it out. But basically, the host portion is any place where there's zeros, right? So if you have a net mask of /27, right, you only have 5 bits of host addresses. And 5 bits, 2 to the 5th minus 1, right? That gives you addresses from 0 to 31. Now, can't use 0, and you can't use the all ones. So really, you can do 1 to 30. So you have 30 usable host IP addresses if you have a /27. Some ISPs hand out much smaller, /29. You get 3 bits, right? So you can represent basically 5 usable IP addresses because you lose one at the top and you lose one at the bottom. Okay? Anyway, so that's that one. All right, so the next one. So we were talking about this 2038 date problem, right? Okay, so here's the way ext4 decided to solve this problem. So one of the things that ext4 introduced was a nanosecond resolution time field, okay? So there's the 32-bit seconds value, which has always been there, and there's this new 32-bit nanosecond resolution field. Okay, nanoseconds, billionths of a second. All right, it turns out you only need 30 bits to represent a billion. I mean, you can do the log base 2 to figure that out. But if you think about it, 32 bits gives you a value that's a little over 4 billion. Okay. If you drop 2 bits, you're basically dividing by 4. And so you get, in 30 bits, a number that's a little over 1 billion. So you need 30 bits to represent nanoseconds. That means we got two spare bits in that nanoseconds field. So what ext4 does is it uses those extra 2 bits to extend the seconds, right? So instead of 32 bits, you've got an extra couple of bits to play around with. Now there's some complexity there, but that's basically the idea. Now, so what that means is that the nanoseconds field in ext4 is a packed structure. The upper 30 bits are the nanoseconds, and the lower 2 bits are the extra seconds for the seconds field, okay? So if you want to see the nanoseconds, so like let's say you're looking at the raw data, right? And that nanoseconds field is this hex value, okay? The upper 30 bits of that are the actual nanoseconds, and the lower 2 bits are the extra seconds. So convert this to binary. I mean, that you can do just by, doing the hex conversion that I showed you earlier. Just go nibble by nibble. So that's this. Then you basically throw away the lower 2 bits, right? You right shift 2. What's left over is the actual nanoseconds value. So once you right shift this 2 places, it's basically, you move the zeros from the end here to the top. And so this is the actual nanoseconds value. Translate that back to hex, it's this 361B60C9. Okay. Plug that into your trusty calculator, and it's that in decimal. And so you can do that with all 4 values. It's basically convert it to binary, move the zeros, convert it back to hex, and then if you want, you can translate it into decimal. Right. Welcome to my world. Yeah. And it's really interesting when ext4 first came out, the tools like ls and stat and things like that hadn't actually caught up to the new reality, and they often got this wrong. And getting it wrong is kind of catastrophic, because not only do you not get the right nanoseconds value if you just treat the whole 32-bit value as nanoseconds, but you also fail for dates after 2038 because you're not picking up the extra seconds that are packed down at the end of that nanoseconds field. So it was kind of an interesting time when ext4 first came out, and the APIs hadn't caught up with this sort of weird packed structure. Anyway, I wrote a blog post about how this time thing works in detail. If you go to my resources page, so down here, I've got a bunch of different breakdowns of different file systems. But this article I actually wrote just recently, more on ext4 timestamps and time stomping. So if you want to learn exactly how those timestamps are used with those extra seconds, I go into detail about that. I also provide you with a tool. I get really sick and tired of people hearing from people that it's impossible to change the creation timestamp and the metadata change timestamp in Unix file systems. Nothing could be easier. Anyway, so I wrote a tool to do it for you. So I wrote a time stomping tool that lets you arbitrarily change timestamps on Unix files. I'm probably going to regret that, but nevertheless, if you're interested, it's this article, more on ext4 timestamps and time stomping. Again, my contact information, that really is my email address. I'm not kidding. And here's my Mastodon handle. Again, if you want to follow me on LinkedIn, that email address will work. Also, a reminder, courseware is Creative Commons licensed. It's up there on my GitHub for anybody to download. If you'd like to share it with coworkers, whatever, please do so. Again, I think we need to stop hoarding information so much. That's why I don't teach for that other training organization anymore. So I realized that it was a priority for me to be able to share this knowledge and all of my courseware. And that was not okay with them. So here we are. I'm training on my own. They're we're both happier. Okay. Anyway, so yes, please feel free to share this courseware with anybody. Okay, not seeing a lot of questions. So let me say again, thank you very much. I hope you learned something, and I hope you had a little bit of fun along the way. And hopefully we'll be able to actually meet up in person, at some event or something. You know what I look like because you've been staring at my little head for the last 4 hours. But I don't know what you look like. So don't be shy about coming up to me if we're at the same event saying, hey, I took your weird little binary class, and let's talk more about binary and hex and computer stuff. And I'm like, okay, cool. So yeah, don't be shy about introducing yourself if we end up at the same event at some time.